Okay, this will be a very quick lecture on Chapter 11, talking about the atomic nature of matter. This particular chapter is fairly important because we're going to talk about what matter is made out of. It's made out of atoms, and then we'll build upon this by talking about solids, liquids, and gases. So I'm not really a chemist. I'm going to talk very briefly about atomic structure, elements, and the periodic table, but again, I am not a chemist and I care more about the result at the end of the day. We'll talk about the sizes of atoms, isotopes, and then really what we care about for the next couple of lectures is going to be compounds and mixtures. Now, we've always been kind of curious about what atom has really been made out of. Even Aristotle said that there's going to be 4 basic elements that make up matter: earth, air, fire, and water. Turns out that it's a little bit more complicated. If you think about taking, say, a large boulder and then breaking it down into smaller rocks and then sand, and then you just keep on splitting and splitting and splitting until you get the most basic building block of matter, it's actually going to be what's called an atom, first postulated by the Greeks in the 5th century, and then we really developed more techniques, and it was in the 1800s and 1900s before we actually could make measurements of these. The biggest problem with making measurements of them is that they're so small that they're actually invisible. And it was in 1827 that a fellow named Robert Brown observed collisions between visible particles that we could see and these invisible creatures that that even the Greeks thought of, that are called atoms. This was later proved by Einstein in the 1900s, proving that there actually are these things called atoms that are the smallest building block of matter. Some basic characteristics of atoms is they're going to be incredibly tiny, very tiny. If you want to compare an atom to, say, an apple, then really an atom is to an apple as an apple is to the planet Earth. So think about the planet Earth and how large it is, and think about an apple and consider the size difference. They're also very numerous. They actually weigh about 10 to the minus 27 kilograms. So to make up something that makes up a kilogram is going to take up 10 to the minus 27, or 10 to the positive 27th of these. So they're very, very, very numerous. They're also always in motion. They're always bouncing back and forth. And I'll talk a little bit as to why in the next couple of lectures. And lastly is that they're ageless. The atoms that are making up you and I today were actually created at the beginning of the universe. So the atoms of, say, my pencil is the same age as the atoms that make up you, even though you're much younger. Really, just these atoms have been transformed from one form into another. How do you rearrange atoms? Well, if you think about striking a match, you're turning some of that wood into smoke. So you're just changing the type of atom that we have, but we're not changing the age of it. So let's take a quick look at the makeup of an atom. Turns out that atoms are going to be what we call electrically neutral. So they're not going to have a net charge associated with them. However, they're comprised of 2 objects that do have some electrical charge associated with them. Charge being kind of like when you can rub your feet on some carpet and make a spark. At the very center of the atom is going to be what's called the nucleus. And the nucleus is extremely small, very, very, very small, 10 to the minus 15th meters. Even though it is very small, it's going to contain most of the atom's mass, 99.975% of it. It's going to be made up of protons and neutrons. They're going to make up kind of the nucleus. And protons are going to have a positive charge associated with them. Now, this charge needs to be kind of balanced out. If you have something that's positive in the center, there needs to be something that is negative associated with it to kind of balance out this electrical charge, because we know that they're electrically neutral. And it turns out that that it's going to have orbiting electrons around it in discrete shells. So these electrons are kind of whizzing around, kind of like orbiting planets around this positive nucleus. And electrons are going to balance the charge out. Now, these electrons actually live in discrete shells, so they're going to live, say, in this one, or in that one. Electrons are never going to kind of just hang out here in between these discrete shells, or orbits, if you will. Now, there's also a limit to the number of electrons in each shell or in each orbit. Essentially, these guys are negatively charged, and opposites are going to attract, so they're going to be drawn into the positive nucleus right here. So they're going to tend to hang out as much as they can in this first shell. Once that shell fills up, then they're going to hop out to the outer shells. Once that shell fills up, then they're going to fill out to that shell right here. Now let's take a look at this nucleus just a little bit more. A nucleus is going to have some number of nucleons, which has a special name. It's going to be the atomic mass number. Really, that's just going to be how many protons we have plus how many neutrons we have. The number of protons is related to what chemists call the atomic number. And if we kind of look at the written form that chemists use, we're going to write, say, carbon. Carbon has 6 protons associated with it, and it has an atomic mass number that is going to be 6 protons plus 6 neutrons. The atomic mass number is going to be 12. So chemists would write this as carbon 12-6. Another type of carbon might have 6 protons and 6 neutrons. This is going to be called an isotope in a couple of slides. So it's going to have an atomic mass number of 6 plus 7. It's going to have an atomic mass number of 13. And chemists would write this as carbon 13, atomic mass number on top, number of protons right down here on the bottom. I'll let you take a quick look at this guy, pause it, and make your own prediction. And then this is going to be the correct answer. Atoms are not manufactured in plants or humans during pregnancy. The correct way, we would say, is these guys are going to be changed. Now, atoms are going to be the basic building block of matter, and when we talk about physical matter, we can talk about a chemical element. So really, atoms, they're just particles that make up a substance that's called an element. These are elemental substances, and they only have one type of atom in them. Remember, what determines the type of an atom is going to be the number of protons. The lightest and most abundant is going to be hydrogen. It only has 1 proton, and it also therefore is going to have typically 1 neutron and 1 electron associated with it. And really, there's about 115 known to date. 90 of them occur in nature, and the remaining 25 or so are pretty unstable. It turns out that as we add more and more protons, the nucleus becomes more and more unwieldy and more unstable, and can tend to decay and also be radioactive. Words like atom and element can be used interchangeably because an element is only going to have one type of atom in it. Now, chemists have gone ahead and they've arranged these elements into what we call a periodic table, which is really kind of a roadmap for chemists. It's not so big in physics, but really it's going to be all of the elements arranged by atomic number in ascending order. Remember, atomic number is related to the number of protons in the nucleus, and it's arranged from left to right such that the number of protons is going to be constantly increasing. Each element is going to be electrically neutral, so it's going to have 1 more proton and 1 more electron than the preceding element. Now, on the far right, there's going to be what's called the noble gases, and essentially these have their outer shells filled to the brim full of electrons. And what that means is these guys are not going to want to share electrons with other elements very well, so they're not going to react very well to them. These are also called inert, in that they tend not to react to other elements. And this is just a quick snapshot of it. So we're going to have ascending number of protons kind of going like that. We're going to have hydrogen. It has a symbol H associated with it. That right there is going to be the number of protons in this guy. And this number right down here is related to its atomic mass, which really is going to be related to the number of protons plus the number of neutrons. And you can kind of see that it goes 1, 2, 3, 4, 5, 6, and so on and so forth. And these guys over here are going to be those gases that tend not to react to other objects. Okay, take a second, pause it, and see if you can answer this guy. We have an atomic number of 44, an atomic mass number of 100. We know that that atomic mass number is going to be equal to the number of protons plus the number of neutrons, and I'm told that this is going to be 100, and this must be equal to 44, so we must have 56 neutrons. Now let's talk about the sizes of atoms. I've said that we have a positive core with these electrons and shells just kind of orbiting it. Really, this nucleus is going to contain most of the mass, but most of the space is going to be just empty air. The diameter is really going to be related to the electrons, or the diameter of the orbits, and really that's kind of related to how much charge is in the center. As we increase the number of protons, we're increasing the electrical charge inside the nucleus, and so that's going to pull the electrons into a smaller orbit. So we would expect, as we increase the number of protons going from left to right in the periodic table, we're going to gradually have smaller and smaller and smaller atoms. Keep in mind that as charge increases, electrons are added to the outer orbits, and the inner orbits are actually going to get smaller. So we can kind of conceptually see the relative sizes of atoms getting smaller as we go across the periodic table here. Now, we know that the number of protons is related to the element that we're talking about. It turns out that we don't necessarily have to have the same number of electrons as protons, or the same number of neutrons as protons. Really, there's just kind of some technical words for this. An ion is going to be a charged atom, and what that means is the atom is going to have more or less electrons than protons. If an atom, say, has 2 protons in the middle, and it's only got 1 electron kind of whizzing around it right there, then it's going to have a deficiency of electrons, so it's only going to have 1 negative charge orbiting it. It's going to have 2 in the center, so it's going to be kind of a net positive ion. We could also have an object that has 1 proton and it's got maybe 2 electrons orbiting it, so it's going to be a net negative charge. Isotopes are going to be where there's a different number of protons and neutrons. It's really going to behave the same exact way, it's just going to have a different number of neutrons associated with it. So take a second and see if you can answer this. It's going to be A. And now we kind of get to the stuff that I really care about, compounds and mixtures. Now, it turns out that these atoms can form chemical bonds with other elements, and when they do, it's going to be called a compound. And it's just made up of different elements. It can be separated into its constituents by chemical means. Let's kind of take a look at salt. Salt is going to be a mixture of sodium and chlorine. So we might write sodium right here. We're going to add some chlorine to it, so we're going to write sodium as NaCl. Note that these guys are sharing electrons, and there is some energy associated with this chemical bond. Now, if you mix together some substances that without chemical bonding them, there's kind of nothing. There's no chemical bond, they're not sharing electrons or anything like that, so there's no energy associated with that. We're just going to call that a mixture. Example of this might be air. It's a mixture of several gases. It's going to be nitrogen, it's got some water vapor, it's got some helium in there, I think. These guys are kind of added together, but they're not sharing electrons, and there's no chemical bond, so there's no energy associated with mixing the gases together. Now, kind of another name for compound is going to be molecule, and that's probably what I'm going to be using a lot more. Molecules are going to be 2 or more atoms that are bound together. Now, they can be the same. They can be like 2 oxygen molecules that are bonded together. They could be different. could be like the sodium chloride on the other slide. It could be NH3, ammonia, 1 nitrogen and 3 oxygens. And keep in mind that there's chemical bonds associated with these. They're sharing electrons, and there's energy associated with them. Something else to keep in mind is that these guys are still in motion. We take a look at water right here. Really, you can kind of pretend that we're going to have that oxygen molecule, and it's going to be attached by springs to this hydrogen molecule. And so these guys are going to be kind of bouncing back and forth on a spring, kind of going back and forth as such. So there is going to always be some motion associated with even molecules. So molecules are perpetually moving. How fast they're moving back and forth, so how fast that hydrogen is moving back and forth, is kind of related to its temperature. If we were to take some water and heat it up, then we're putting energy into the system. That energy kind of goes into that spring right there, and this hydrogen is going to increase how fast it's going back and forth, as well as how far it goes back and forth. Now we can rearrange molecules through means of a chemical reaction in which we play games with the atoms that make up that molecule. Now let's just take a look at CO2. We're going to have a carbon with 2 oxygens kind of attached to it. Keep in mind that these guys are attached by, you kind of conceptually think of it as by springs, and it takes energy to say take this CO2 and pull it apart, to break that bond, to essentially take that string and to take that spring and rip it apart. It takes energy in order to break the bonds of CO2 to produce oxygen and carbon. Combining atoms similarly is going to release energy. And of course, now it's time for your lab, and the quiz will be next class. Don't forget that I've technically now covered Chapter 11, so homework 11 is due next class.